Okay, in this piece, we want to talk about the relationship between the electric potential and the electric field. And if you remember the map of things, both of these things were an influence of the electric charges. The electric potential and the electric field are both influenced. And we said that you can calculate the electric field if you know the electric potential over all space. You can figure out what the electric field is by performing this operation. This operation says that the electric field is negative the gradient of the electric potential, and that's what we'll think about in this story. By the way, if you want to go backwards, you can do that. You can integrate the electric field to find the electric potential difference, but we're not going to be talking about in this particular video. So what does a gradient mean? A gradient is kind of a generalized word for the slope. You know what a slope is? Typically, the slope, we talk about the slope of a line or the slope of a surface, etc. So the electric field can be thought of as the slope of the electric potential. Now, if you think about, okay, you're on top of a mountain, for example, and you think about going from, let's say, 50 meters above sea level to 40 meters above sea level. Now, there are places where you can go down on a very shallow part, and there are pieces where you can go down on a very steep part. So it's really about how far do you drop and how much distance. That's really what gives you the slope. And the electric field is the same kind of thing, but in relation to the electric potential. So if you know if I move between 2 points and I drop a certain amount of potential and a certain amount of distance, that will tell me something about the electric field. So let's explore that concept. So suppose I'm just going to think about one dimension for now, and that dimension could be anything, x, y, etc. So we just call it S. It just represents some dimension that is like a displacement dimension in some direction. So I say, suppose I'm thinking about the potential as a function of that particular dimension. And let's say it's given by some kind of curve like that. So of course it could have any kind of shape. And we're going to think about it using that particular shape, let's say. And then I say, suppose I want to find out what is the average electric field between 2 points. So when I think about the potential difference between the 2 points, and I want to ask the question, on average, how steep is this curve between these 2 points, S1 and S2? So I know what the potential at S1 is, I know what the potential at S2 is, but what on average, what is the steepness? Obviously, it's much steeper at the top here, less steep at the bottom. But if I want to ask the question, on average, how steep is the electric potential curve between these 2 points? Then I would do some operation like this. I would, let's say, connect them by a line, and I say, what is the slope of that line? So I want to find out how much I'm dropping in potential in how much distance. And then we define the average electric field between these 2 points as how much you dropped in potential divided by how far did you have to go to drop that much. The negative sign has to do with the direction information. This negative sign is basically saying that the electric field direction is always from high potential to low potential. So if I want to just think about the magnitude would be the voltage drop or the voltage difference between the 2 points divided by the displacement or distance between the 2 points along that particular dimension. But the negative S hat is telling me about the direction of the average electric field, and it's telling me that it's always, always, always pointing from high potential to low potential. Now, if I shrink this a lot, if I shrink delta S a lot and I turn it into an infinitesimal piece in the limit that delta S becomes really, really small, like an infinitesimal ds, then we speak of something called the local electric field at some point. So at some point S3, for example, if I make this triangle so small that you almost can't see it, the ds, then I'm talking about the slope of the tangent to the line, and in which case we represent it by the derivative. Represented by the derivative of the potential with respect to that particular dimension, and that's the local electric field at that point. Think of it, because this was a story about the average electric field over some region. But if I want to say at this particular point, what's the electric field, then you make delta S so small, becomes infinitesimal, and you say roughly how much does the potential change when I change by very little in that particular dimension. And that's really what the gradient is. So the derivative of the potential in the dimension, the gradient is just a representation of that in higher dimensions when you have to think about the slope in multiple directions. Because if you are on the side of a mountain, for example, you can go east, and then that means you're climbing down or climbing up at a particular steepness. If you go to the direction north, then you're climbing up or down at a different steepness, and so on. So you have to play that game depending on which direction you're going. So let me tell you about this operator here. Sometimes it's called the del operator, sometimes it's called nabla operator. It's a del operator, but in this particular case, we're using it to represent the gradient. And the gradient is about the steepest slope. Now I can do that and depending on what coordinate system you use. You can use a Cartesian coordinate system to describe the gradient, or you can use the spherical coordinate system to describe the gradient. You would use the Cartesian coordinate system to describe the gradient of the particular function you want to take the gradient of is given to you in terms of its Cartesian coordinates, x, y, and z. So you think of this particular function here, let's call it f, that has some value over all space. So whatever location you put in here gives you the value of the function. But I want to take the gradient of that function. So I want to know its slope at some particular point. How do I find that? Well, you take something called the partial derivative of that function with respect to x in the x direction, the partial derivative with respect to y in the y direction, plus the partial derivative with respect to z in the z direction. The partial derivative, what it means is that ignore the change in any other direction. So really what it's saying, it's a very simple statement. It just looks a little scary, but it's a really simple statement. All it's saying is to find the steepest slope at any point for that function, what you have to do is to say, how much would I change the function by if I move a little bit in the x direction? And how much would that function change if I move a little bit in the y direction? How much is the function going to change if I move a little bit in the z direction? But each one of those would be multiplied by that direction. So if I change a lot in the x, then I say, okay, there's a lot of change. If I move in x, the function changes a lot in that I hat. And if it changes in the y direction, then I have to put that change in the y. So notice that the gradient then takes a scalar function and turns it into a vector. It's the vector that says what is the steepest slope of that function at that particular location. You do the same thing, of course, for spherical coordinates, but now the spherical coordinates, remember, are r, which is how far you are away from that origin. And then you have two angles, the azimuthal angle and the angle. And this is written in terms of r theta and phi. And then the del function then is written as the partial derivative of the function with respect to the r, with respect to the distance away from the origin in that direction, in that radial direction, plus 1 over r times. So notice this is different than its form in the Cartesian coordinates. 1 over r partial f by partial theta in the theta hat, 1 over r sine theta partial f by partial phi in the phi hat direction. Let me show you some examples that'll make it clearer. So suppose I think about the Cartesian representation. So for example, suppose I have a function h that has value over all locations. So if you put x, y, and z, it tells you the value of the function h. Turns out that x and z don't affect the function. So the function is the same for all x and for all z. Whatever x you put, you get the same outcome. It's really the y that changes the function. So you say this function looks like ay plus b, for example, where a and b are constants. So say it only depends on what the y value is. What is the gradient of that function at any location in general? If I want to know at a specific location, then once I find the gradient, I can plug in that location. But first, let's find the gradient symbolically. So the way to think about it then is to say the gradient of h is given by this expression for h, partial by h by partial x in the x, partial h by partial y in the y, partial h by partial z in the z. Now, because it doesn't depend on x anywhere, then its derivative with respect to x is 0. Because when I take the derivative of h with respect to x, I pretend that y is constant and z is constant if it's in the equation. So now none of these explicitly depend on x. So the derivative then would be 0. But the derivative with respect to y is the constant in front of y here because y has a unit power. So I just get a in the y direction. And then, of course, when I take with respect to z, because there's no explicit dependent on z, then I get 0 in the z direction. So then the gradient of this function is only going to be in the y direction. Makes sense, because if you're moving in x or z, you're not going up or down because it doesn't depend on x and z. If you're moving in y, then you're moving by a certain amount, you're dropping by a certain amount, and that amount is a for every 1 meter you walk in the y direction. Here's another example. again with Cartesian coordinates, where the function depends explicitly on x and y and z with some kind of polynomial dependence. So again, I do the same kind of story. I do the same kind of story where I think about the partial derivative of the function with respect to x, with respect to y, and with respect to z. So with respect to x, I pretend that y is constant and I pretend that z is constant. So the derivative of that first term then becomes a times y squared, because only x is the variable. And then the derivative of the second term then would be z times twice x. So that's in the x direction. If I'm taking its derivative with respect to y, then this term obviously doesn't depend on y, so it's going to go away. And this term I'm going to get twice ax times the y. So ax is a constant up front, and the derivative of y squared is twice y. So I get twice ax times the y in the y direction. And then, of course, when I take the derivative with respect to z, only this term is going to count. This term is going to go to 0 because it doesn't explicitly depend on z. So I get the derivative to be just the coefficient of z because it has unit power. So that's how you take the partial derivative, which is known, and that's how you calculate the gradient of some function, of some scalar function, to find the vector that represents the direction of the steepest slope of that function. What about in spherical coordinates? Suppose I think about a function that looks something like this. Just any kind of like arbitrary function. Let's pick, for example, r sine phi. And I want to ask myself, how do I calculate this gradient for this particular function? So again, the same kind of story where you take the partial derivative with respect to r. So you say, okay, sine phi, because r has unit power. So whatever the constant in front of it. So that's what this term looks like. And then in this term, once I take the derivative with respect to theta, I still have to divide by 1 over r. In this case, though, there is no dependence on theta. So this partial derivative would be 0, and 1 over r times 0 would just be 0. So this term would be 0. In this term, when I look at the derivative of the function with respect to phi, I say, oh, hang on a second. This depends on phi, and the derivative of sine phi is cosine phi, and then the r up front is constant, so it becomes r cosine phi, and I have to divide by r sine theta. So this becomes r cosine phi divided by r sine theta. The derivative of the sine is cosine. Yes, this negative sign is incorrect. Here's another example where the function in the spherical coordinates only depends on the r. It doesn't depend on the theta or the phi. So it's some kind of constant divided by r plus some kind of constant, a shift. So you say, okay, hang on a second. If I take the derivative of this with respect to r, because it's 1 over r, the derivative of 1 over r is negative 1 over r squared. So this term is going to look like negative 1 over r squared times whatever the constants are. And of course, the constant term, when I take the derivative out, it goes to 0. When I take the derivative with respect to theta, it becomes 0. And when I take the derivative with respect to phi, then it's 0. Then that's it. This is it. This is the only dependence that depends only on r. And then I say, hang on a second. I recognize this. When I say V of is equal to kq over r, I know what that is. That's the potential due to a point charge. So when I take the gradient of that potential due to a point charge, I get the electric field because that's the relationship. So I say, suppose the potential is kq over r, and I take the gradient, I get negative kq over r squared in the r hat. But because the expression says the electric field is the negative of the gradient, then this negative sign goes away, and I'm left with the electric field due to a point charge is kq over r squared in the direction r hat. And we'll explore this more when we talk about the electric field.